course, she's got her runny nose and she's Daddy, don't leave. So I was running later than I was hoping. Okay. Let's go ahead and get started here. See if I can set this up where people at home can follow. I was going to try to do a split screen by screaming Logitech there. And that way you'd have like me talking with the PowerPoint in the background, but I'm having a hard time getting Logitech to communicate with YouTube. And I'll figure that out. I can do this. I need more than 2 minutes to do it. So we had our first test on this last weekend. Everything went okay with it? Yeah, pretty straightforward. Yeah, good. Just remember on those essay questions, when you'll have another test with me on those essay questions, since we are take-home, open book, open note with really no time limits, just make sure that you answer those questions thoroughly. That's all that I ask, all right, and the TAs will be grading it over the next week or so give them some time to grade it. I sent them the answer keys. They should start working on that pretty soon. All right. Okay. So no questions about the test or anything? We're all good? Okay, and you guys at home, if you have any questions, you can also hit me up on the top chat here on YouTube, and I'll see if I can get to it. All right, so we have basically just a few weeks left. I think something like 3 weeks. And then this next 3 till spring break, and then I'm gone, and then you get a new teacher, Dr. Kuhn Adama. That's why I said only 3 weeks with me. The class continues on for the rest of the semester. Don't worry. It's just with me. So we're going to finish out chapter 6 on lipids. And lipids also, we're going to talk about membranes, the first cells, and one other thing, which is transport. This thing is in my way here. Okay. There we go. And transport. And transport, I'm going to add in a little bit of what's not in the book. The book is really, really light on transport. They don't talk about uniports, symports, and antiports and co-transport, which is actually like really important to know those differences. So we'll get to them on Thursday. And today we're just going to talk about the structure and function of lipids. And then that basically gives me 4 lectures, 2 weeks to cover cells, which or eukaryotic cell structure and function. And that's just fascinating, thinking about the structure and function of all those organelles inside eukaryotic cells. And I'm also going to expand on on that a little bit, especially in terms of like aging and longevity. And I'll also expand a little bit on the prokaryotes and talk a little bit about prokaryotic diversity, which is pretty fascinating. I mean, they get glossed over in our books because, well, they're much more structurally simple than a eukaryotic cell, but they're fascinating in terms of their metabolism. I mean, there's bacteria that can eat rocks, right, and live in battery acid or in freezing temperatures or in hot springs that you can boil water in, right? And of course, our gut microbiome is incredibly dependent on all the bacteria that live in there with us. So we'll expand on that quite a bit. Okay, any questions? All right. Well, here we go. We got lipids. Let's talk about lipids. So I'm showing the clip art, I guess, of a triglyceride, a phospholipid, and steroids, and waxes. Nope, wrong computer, of course. So what we're going to talk about, structure and function. I mean, structure and function matter from molecules up to the organisms themselves. So we're going to talk about how the structure of a lipid affects its function. Pretty straightforward, right? And then we'll get to membranes, membrane transport, and understand the importance of membranes in abiogenesis. And today, like I said, we're going to focus on structure and function of lipids. And of course, this is the many roles of lipids. Do you guys recognize this molecule? What can you tell me about it? What does it look like?
Sugar or carbohydrates?
Well, do we see a ring structure, any hydroxyl groups or anything in there? So we get these long chains. This node right here, what does that represent? You guys are forgetting your organic chemistry already, or just tired of shell shock after taking the test, right? That's a carbon right there, isn't it? That's a covalent bond between carbons. And what are we missing? What are we not showing here? Hydrogens. We get these three long tails with the carboxyl group at the end. This would be a fatty acid. We got three of them, so that's tri. This is a molecule of glycerol. That's a triglyceride. It's fat. And fats store energy. So I noticed that on me, this is getting a little bit larger. I'm having to change up some things I'm doing, like some restricting when I eat to reduce this right here, which is made up of fatty acids stored in adipose tissue. Adipose tissue, of course, are your fat cells. So this is a long-term source of energy because it's full of carbon and hydrogen, and the energy is stored, of course, in the bonds between the carbon and the hydrogen. So lipids, they're used for energy storage. This molecule is cholesterol. And cholesterol, right here, is a class of molecules called the sterols. And you can recognize them. You've got these four rings, two hexagonal rings attached to another hexagonal and a pentagonal ring here. And then how you change these functional groups in there and there will determine the difference between something like estrogen, testosterone, right? There's very small differences between testosterone and estrogen, but just small changes in those functional groups, you know, that changes how these molecules are perceived by our cells and elicits different cellular responses. So hormones like testosterone and estrogen, they're used for signaling. And of course, I forgot to change fats and energy storage. This is supposed to be a signaling molecule. Sorry about that. I'll fix that. And of course, membranes. Cypress Hill, insane in the brain. Insane in the membrane. My daughter loves that video. It's pretty funny. Okay. Cells are the basic unit of life, right? And cells are a system that's out of equilibrium with its environment. And when we start talking about cells as a system is defined by a boundary. And that boundary here is the membrane. And that membrane separates the living cell, the inside components, and all those interacting metabolic reactions and all other things happening inside the cell. The membrane separates that part of the cell from the outside world. And the structure of the membranes really affect its function. And we're going to talk a lot about membranes and how you change the fatty acids in there to affect fluidity, how that affects permeability. And then we're going to talk about a lot of the different types of proteins embedded in the membranes that allow membranes to move substances across its surface, because cells have to regulate what comes in and what goes out. And there's lots of ways they do that. And one of the reasons why I'm going to talk about antiports, symports, uniports, co-transport, and all that stuff that's not in this chapter is because that stuff is in plant and animal form and function. And they talk about it in those later chapters, but failed to introduce it in this chapter, which the people that wrote the animal physiology part and the plant physiology did not talk to the people that wrote this chapter. And it's quite clear that, and after teaching all of these classes, cell and molecular ecology and evolution, which is 303, and plant animal form and function, which is 304, you kind of see where there's a miscommunication. So I'm going to give you guys a running head start in 304. Good? Yeah. You guys all want to take 304, right? Yeah, that's a pretty cool class. I like 303. I love this class. I like them all. All right. Let's take look at this molecule here. These two molecules. Doesn't that look like cholesterol? Pretty close, isn't it? That's your sterols. That's the difference in functional groups that are affecting its function. This, of course, remember this one? Triglyceride. Triglycerides are fats. Okay, what are the two most common elements in these molecules? Carbon and hydrogen. Now that tells you something about this molecule. Is it hydrophobic or hydrophilic? It's hydrophobic. Does it store, excuse me, does it store a lot of potential energy or little potential energy? That's a tough one, isn't it? Remember that potential energy is stored in the bonds of molecules. Okay? These two bonds are non-polar covalent bonds. Carbon and carbon, of course, have the same electronegativity, right? What that means is these electrons are shared equally between the two carbons. Your potential energy stored in the bonds is a function of the distance of the electrons from the nucleus. The further away an electron is from the nucleus, the more energy it has. Non-polar covalent bonds, same electronegativities, right smack in the middle of the two elements. The electrons are furthest away from the nucleus. They store the most potential energy. These are really, really similar, so they also store a lot of potential energy as well. And then nitrogen has 7 protons, the carbon's 6 protons. So this, of course, is a polar covalent bond. This stores less energy than these two. And then carbon and oxygen is an even stronger covalent bond because oxygen is even more electronegative than nitrogen or carbon. So oxygen's holding on to those electrons tightly. That bond stores much less energy. Good? Okay, and that's exactly why when you look at like a triglyceride, that's why it stores so much more energy than a carbohydrate. Okay. So when you take a look at these things, we've got our sterols here. This one's testosterone. This is used for chemical signaling. This is a triglyceride. This is a fat used for energy storage. And this is a phospholipid. And this is used to form our membranes. So you see these long fatty acid tails. And as you realize, those fatty acid tails are hydrophobic. When we start talking about membranes, that will become much more important. Okay. Hydrophobic or hydrophilic, either water-fearing or water-loving. However, like many things, it's not either or. There's a range, right? You can be really hydrophilic, like water molecule or methanol. So if I drew up something like methanol, this molecule is fairly hydrophilic, right? But if I were to draw something like butanol, this is less hydrophilic because you've got more carbon and hydrogen here. And then if I were to draw something like I don't know, how many is that? 1, 2, 3, 4, 5, 6, 7, 8. A very short chain fatty acid here. I've got the carboxyl group instead of a OH group. If I just had a hydroxyl, it'd be an octanol. But this is now a fatty acid because I have a carboxyl group. This is even less hydrophilic. And in fact, we would start to call something like this amphipathic, which amphi means like both, like amphibians live on water and on land. This end is hydrophilic, and then the tail here would be, of course, hydrophobic. Okay, so what I'm saying here is that a lipid, all that carbon and hydrogen forming non-polar covalent bonds, it can't form hydrogen bonds with water, it's hydrophobic. However, you can take a molecule like this is a cholesterol or a steroid here, and you get the little hydroxyl group at the end. That hydroxyl group is hydrophilic. It can form hydrogen bonds with water. This is hydrophilic. This can form hydrogen bonds with water. So this end will mix with water. This end won't. And of course, that little hydroxyl group is very important for how like cholesterol gets into your membranes. And actually, it's a very important component of your cellular membranes, because that's this hydrophobic part is gonna mix in down there with all the fatty acids. The little hydroxyl group will be on the outside of the membrane interacting with water. So fatty acids, so lipids are mostly hydrophobic, but by the addition of various functional groups to parts of them, you can make part of that lipid hydrophilic. And that makes it empathic, so they have both hydrophobic regions and a hydrophilic region, or at least a hydrophilic end. Okay? Form and function matter, theme in biology. Okay. So let's talk a little bit about sterols. This is cholesterol. It is estrogen. It is testosterone, and amongst other things as well. And in fact, estrogen, there's different types of estrogens that are involved with hormones. I love this to compare these two, right? I mean, if you are reaching puberty and you start producing lots of this, or lots of this, or even actually in development, when you're an embryo, whether or not you have a Y chromosome or two X's, the Y chromosome has something called the sex determining region of the Y, the SRY region. And the SRY region turns on a lot of different genes and turns off others. It takes a female embryo, turns it male. Guys, we're a derived female. It's okay. I'm cool with that. But part of that change is the production of testosterone, which takes a female embryo as part of the process. It's more complicated than just releasing testosterone. But basically, this is the difference between boy and girl. And look at this. I mean, here's got a carbonyl group, a hydroxyl group. This one's got no methyl group here, but it's got a double bond there, which means that ring is flattened. And then you've got an extra hydroxyl group up here on this end. So these molecules, the basic ring structure is exactly the same, except the position of hydroxyl groups, carbonyl groups, the loss of a methyl group, or the addition of rings, of double bonds in the ring would flatten those rings. That changes the shape of this molecule, so it has different receptors inside of your cells and elicits different responses in your cells. This makes bones grow thicker, muscles grow longer, increases hair growth, adds muscle, right? So, yeah, the functional groups really matter here. Okay. So shape matters. Oh. And I'm outlining there where those two different groups are. So for you guys at home, you can see that the red box right there is showing the difference between the methyl groups and not having them. Or a hydroxyl group and a carbonyl group. It's amazing, right? Small differences matter. That's the mountain. You guys ever watch Game of Thrones? just don't watch the last season and you'll be okay. Especially the last episode. And it's not family friendly, so if you don't like violence, skip it. It was a little, yeah, we don't have to talk about it. But this guy played the Mountain. I can't pronounce his name. I feel really bad. But this guy weighs about 400 pounds and he's squatting 845 pounds. This is the role of testosterone in building muscle. And a lot of athletes will take additional testosterone. They'll, as one of their steroids, to increase muscle growth and bone growth. Interestingly, that's not the only reason why you can take testosterone. As men get older, our testosterone levels tend to decrease as with age, and that can lead to muscle loss, smaller bones, and depression, actually. So they do make testosterone and prescribe it for legitimate reasons. And also, people that get cancer or on chemo or become very sickly, they will also prescribe testosterone to help build muscle. I know a guy in high school, he had cancer, he had leukemia, and they prescribed him testosterone so he could maintain a normal body weight because the chemo was pretty brutal. Yeah, 400 pounds, squatting 845. I have comments to say, but I'm not going to say anything. I had a 600-pound squat lift at 180. Pound for pound, I was stronger than that dude. But 800 pounds would crush me like a paperweight, though. Yeah, and then some people take anabolic steroids to, of course, grow large muscles. There are legitimate reasons, like I said, that you can have steroids prescribed. Of course, that's what's his name, Ronnie Coleman, that won like however many bodybuilding contests. It was ridiculous. This guy, he actually had like some real breakdowns, and his arms actually got infected from all the steroid injections. So, if you ever think about doing something like that, consult your doctor, because there are problems associated with that as well. Okay, cholesterol. This is a related compound. This is actually the precursors here. You guys have heard of like good cholesterol, bad cholesterol, right? Okay, first of all, we need to have some clarification here. There's no real such thing as good cholesterol, bad cholesterol. It's all cholesterol. You probably have heard of LDLs and HDLs, right? Low density lipoprotein, high density lipoprotein. This is our way of talking about good cholesterol, bad cholesterol. Cholesterol, we get it from our diet and we make it in our liver. And our cells need it in their membrane because it helps regulate our membrane fluidity and permeability, okay? And we need to, like I said, all cells have to regulate what's coming in and out of their membranes, in and out of their cells. So in animals, we have cholesterol as one of those molecules that is used to, like I said, regulate what can go across the cell membrane. All right, so think about this. You're absorbing cholesterol somewhat through your blood, but you're making it through your liver, and you've got to transport cholesterol from your liver to other regions of your body. Now, the way you're going to transport that is through your blood, right? Blood is mostly water. So if you've got blood that's mostly water, how do you transport a molecule that's hydrophobic? Well, you stick it in a protein. And in this case, this is the simple version, LDLs and HDLs. There's lots of different types of HDLs and LDLs. There's not the two of them, there's extras. But basically, to keep it kind of simple here, these are transport molecules that have a hydrophobic interior where you store your cholesterol molecules with a hydrophilic exterior so it can move through your blood, okay? Now, this is the LDL. This is the low density lipoprotein. This protein carries cholesterol from your liver to your cells, okay? HDLs remove cholesterol. They take cholesterol away and take it back to your liver so it can, do whatever the liver is going to do with it. Now we know that you've probably heard that the LDLs are bad and HDLs are the good cholesterol. And if you go get your blood work, which you should do, even in your 20s, it's like peeking under the hood to see what's going on with your body. It's a good idea to get your blood work done even at an early age, because you can spot problems early and prevent the long-term consequences of these things. So you'll get like a total cholesterol back. And your total cholesterol is built on your LDL and your HDLs. And what you want to have is a higher HDL compared to your LDLs. And the reason why we call the LDL, the low density lipoprotein, bad cholesterol, is because LDLs can accumulate as plaque in your arteries. Okay? Now your arteries, of course, are taking blood away from your heart. And every time your heart beats, you can feel those arteries expand like this. They're supposed to be elastic. All right? And what happens is if you have a high amount of LDLs, they can build up in those arteries and form plaques. You get what's called atherosclerotic plaque. It's an LDL accumulation. And you can see that the passageway becomes narrow. And as it becomes narrow, the blood doesn't flow through there as well. That causes problems. You get less blood flow. Your heart has to work harder. And if you clog that artery, you can have a heart attack and you can actually die. Heart attacks. Heart disease kills people every day. I mean, rate of heart disease up until COVID this last year is probably the #1 killer of people in our country. So the HDL, this helps regulate the LDL storage, and it helps get rid of and remove the LDLs and prevents plaque. So that's why it's a good idea, because there are genetic mutations where people inherit a genetic mutation for what's called hypercholesterolemia. If you've ever heard of hypercholesterolemia, these LDLs, if you notice, let me go back up a slide here really quick. If you notice, there's proteins on the surface of these things. And what happens is on the LDL, when they go to your cells, you have a receptor. And that receptor helps bind to the LDL and bring the cholesterol into the membrane or into the cell, and it can be repositioned in the membrane. I'm not sure exactly how that works, but you have to have a cholesterol receptor. If you have the mild form of hypercholesterolemia, you produce about half the number of receptors as you need. So you have high cholesterol. And you're probably going to die of a heart attack in your 40s. It doesn't matter if you're a marathon runner and a vegan. You'll probably die of a heart attack. You might push it out another 5 years or so. If you have the full-blown disease of hypercholesterolemia, the full-blown, you don't produce those LDLs. You die in your 20s of a heart attack. You could be a vegan marathon runner, and you'll still die of a heart attack. It's pretty crazy, isn't it? And we can actually control your cholesterol with drugs like statins. So like I said, it's always a good idea to take a look at your blood work and know what your cholesterol levels are, which include both LDLs and HDLs. And if there's problems, you can make lifestyle changes. You can change your diet. You can change your exercise. You can change when you eat. And in fact, that's what I'm working on right now. Is I suck at dieting, totally. I eat pizza. I drink beer. It happens. It's just the way it is. And, so what I'm trying to do is restrict when I eat. I try to have an 8-hour winding, an 8-hour feeding period. I know it sounds so weird, like what you do to your dogs or your fish or something. But I try to eat between 10 and 6, if that makes sense. And fast for the other 16 hours of the day. You gotta do the math. Man, it's hard doing math in your head straight up. Okay, yeah. So if you have problems with this, and triglycerides, which is another one. If you have a lot of sugar in your diet, you might have high triglycerides in your blood. So like I said, it's always good to take a peek under the hood and see what's going on. I eat a salad every day. I had croutons, a little bit of cheese to it. I tried to do balsamic vinaigrette because I really like the fatty dressings. And that kind of defeats a fatty diet though. But vegetables will help that. I grind a lot of mine up into smoothies with fruit and yogurt. I'm not a big vegetable eater. But you can also eat nuts. Turns out a handful of nuts, not just peanuts, but all the good ones, the almonds and macadamia nuts and hazelnuts and walnuts. These actually have lots of, we're going to talk about these. They have lots of what's called polyunsaturated fats, like what you would find in olive oil or in cold water fish. And like I said, these can actually improve the ratio of HDLs to LDLs by lowering the LDL levels. And that's what's really important. So about before COVID, my cholesterol was at like 190, and I was like, oh, it's getting high. And the nurse was like, no, you're like in your mid 40s, your LDLs are very low and your HDLs are high for your age. She said, you had the blood work of somebody in their 20s. Good job. Keep doing what you're doing. And I eat fish and pine nuts, but I also walk about 600 miles each year, which really helps out too. I have a hiking app. Yeah, I know, I get an app. I also have an app to count my steps too. Okay. Are we good with the LDLs, HDLs? Yeah, I mean, I'm going to encourage you guys to, like I said, go get your blood work done. It's very, very informative about your health and can help you out with help identify problems ahead of time. Okay, so those are sterols. Let's talk about fats now. Okay, so I've got a glycerol molecule at the top. This is our fatty acid. As you can see, it carries a lot of potential energy. You know, octane only has 1, 2, 3, 4, 5, 6, 7, 8. That's like octane right here. This is a component of gasoline. This is your fatty acids, right? Stores a lot of energy. And of course, you combine a fatty acid with a molecule of glycerol through a dehydration reaction. We've seen these before. You link amino acids to form a protein, dehydration reaction. You link glucose molecules to form starch or glycogen or cellulose, dehydration reaction. You take your nucleotides, adenine, thymine, guanine, cytosine, link them together, dehydration reaction. Now, here's a key difference. Proteins, carbs, nucleic acids are polymers. Linked together, smaller building blocks to these larger and larger and larger chains. They are polymers. This is not a polymer. Because once you link the three fatty acids together to the glycerol, you're done. That's it. It's over with. Whereas, you know, proteins and nucleic acids and your cellulose and starch, they can be larger and larger and larger and larger, depending on what you're doing. But once you get them linked together, that's it. Okay. One thing that's important here, especially when we start talking about membranes, is the difference between an ether and an ester linkage. So if I've got, this is glycerol. It's got the 3 hydroxyl groups, and I'm just gonna skip out on the hydrogens there. I'm lazy. Then let's say I've got a fatty acid. I'm just gonna draw the chain like that. And you guys know what this chain represents, right? Covalent bonds, carbon, hydrogen here, you get the idea. Okay, so when I do my dehydration reaction, we're gonna do it like that, and then water comes out of here like this. So I've got what is now carbon, oxygen, oxygen, carbon, carbon, oxygen, carbon, double bonded to the oxygen right there. This, of course, is an ester bond. Okay? So fatty acids are linked together with a dehydration reaction that creates an ester linkage between the glycerol and the fatty acid. Okay? All right. And then there's a full triglyceride. And notice I'm calling it saturated. It means it's saturated in something, isn't it? So if I have something that's saturated, it means I probably have something that's unsaturated. And if you notice, this one is straight. These are all single covalent bonds. And notice the difference right there. So what is this one unsaturated in? Or let me ask this. What is this molecule saturated in compared to the unsaturated fat? Hydrogen, exactly, yeah. Yeah, this one's missing a hydrogen. It's missing two, actually. That means it has less potential energy. But more importantly, do you see something else different about it? Shape is different. That form and function, I mean, it's so important. Oh, come on. Play. All right, they say never use sound, but I tried. Oh, come on, I can do this. On, oh. All right. It was supposed to play the theme song from Good, Bad, and the Ugly. Of course, I can't get the sound to turn on in here. I always seem to have that problem. Sing it. The Good, Bad, and the Ugly? Sure. Ennio Morricone? I don't think so. It's instrumental. I just wanted to show you guys, some of the most unique sounds of all time in a movie. And it was the first movie to ever have a theme for each of the main characters. So, of course, Clint Eastwood here had his theme as the good. Lee Van Cleef had his theme as the bad. And horrible. I forgot the name of the actor that played the ugly, but he had his own theme as well. And of course, John Williams copied that when he did this little movie in 1977 called Star Wars. Okay, the point here is fats are not all the same. As you can see, I've got three different types: unsaturated, the good; saturated, the bad; and trans fats are the ugly. Let's take a good look here. An unsaturated fat are what we consider good fats. You need them in your diet. Now, that being said, it's all about moderation, right? Don't go drink a bottle of olive oil every day thinking you're going to be healthy, because that is a ridiculous amount of calories and it would not be helpful in your health. However, pouring some olive oil on your salad is a very good idea. Okay, and also, like I said, a handful of mixed nuts is also incredibly important for your nutrition. There are multiple studies coming out saying that a handful of nuts helps lower LDL levels, improve cognition, and that these corollary studies have shown that people that eat nuts tend to live longer than people that don't eat nuts. And I'm careful to say this is a corollary study. It could be lifestyle as well, but I think the data is coming out that they're actually very good for you. And of course, we're unsaturated because we have those there's double bonds in the carbon right here, which basically causes these tails to bend, okay? That bending is very important. And the reason why is because these tails aren't bent. These fatty acid tails can't stack on top of each other. And fatty acids, even though they are mostly hydrophobic, they can stick together through van der Waals forces. And in fact, that's why butter is a solid at room temperature. That's why earwax is solid. It's not hydrogen bonding, it's van der Waals forces. Weaker than hydrogen bonding, but they add up, right? This prevents them from being solid. It prevents them from stacking together. So a polyunsaturated fat will be liquid at room temperature. There's a couple of different ways to think about this. I see you guys taking notes on your paper. Your paper is flat. It stacks. So you can take a couple pages, rip them up, and crush them up. They have about the same amount of energy, right? This has almost the same as energy, a little bit less because it's missing, these hydrogens right here. But if I wad my paper up, I change the shape of it, and you can't stack 200 pieces of wadded up paper on your desk, right? So because they don't stack, they stay liquid. They're not as dense. You don't have as much energy in the same volume. And another thing, you ever go to make a fire, right? Do you just take the entire newspaper without wadding it up and try to light it? You ever try to light a book on fire? It doesn't work so well. Don't ever light books on fire. That's awful. I saw that when I was a kid. It was terrible. But the idea is it's really hard to take the paper that's all stacked because it's hard for the oxygen to get in there and for it to break down. Likewise, in a saturated fat, if they're sticking on together, it's harder for your enzymes to break it down, whereas here it's easier for your enzymes to break it down. So lots of reasons why this is also good for us. And of course, you can get it from olive oil, mixed nuts, and cold water fish. And we talk about membranes, I'll explain why cold water fish are such a great source of polyunsaturated fats. And of course, we need a couple, omega-3 and omega-6s, an essential nutrient, an essential amino acid, an essential fatty acid means we have to have it, but we can't make it. And that is very different from walking into some frumpy health store, talks about essential oils. No. Essential is something you have to have, like an amino acid that we can't make, or omega-3 and omega-6s. And here's how they get their name. You guys know what omega means, right? I am alpha, I'm omega, I'm the first, I am the last. Omega, this is your omega carbon. It's the last. Omega-3, 1, 2, 3. There's your double bond. Omega-6, 1, 2, 3, 4, 5, 6. There's your double bond. And for whatever reasons, we don't have the metabolism to make that, but we need it. Okay? All right. Man, I had French fries yesterday. And my wife went grocery shopping, and she had a little package, a little tea set for my daughter, right? And she's hiding it behind her back. And she goes, "What do you think I have?" And my daughter, my 4-year-old, goes, "Donuts." Damn it. They're so yummy, right? These saturated fats taste so good. They're generally considered unhealthy. They're not that good for you. And like I said, what's going on with saturated fats is they're saturated in carbon. There's the fatty acids themselves are straight, like this. And because they're straight, what they can do is they can stack, and van der Waals forces will help hold them together. So you can stack them in your fat cells. They store lots of energy, and they're harder to break down. And of course, these things also lead to plaques, artery disease, and whatnot. The thing about that is, as I just admitted to you guys, I don't eat donuts that much. Not that big. I like them, but I don't eat them that much. But I do eat pizza. I do like my French fries. And a green chili cheeseburger is one of the greatest things in the world, right? Go New Mexico. Green chili is awesome. Goes good on everything. Now, that being said, I don't eat hamburgers every day. I don't eat bacon every day. Bacon is like once a month, a hamburger every few weeks. And the idea here is that you can have some of this, just watch out how much you eat of it. The world is about moderation, right? And in fact, there's even been some studies that shows that saturated fats may not be as bad for us as we originally thought, may even be in small quantities beneficial. I think those studies, the jury is still out on those. I would work to cut that back. Notice I said cut back. Watch how much, moderate, do what's best for you. If you're eating a burger a week and your blood work is fine, keep doing what you're doing. If you're eating 3 burgers a week, and 3 or 4 Mountain Dews a day, and your triglycerides come back high, you got to make changes. I know. Well, graduate school, right? I just pounded my regular Mountain Dew and ate pizza every day. And if I ate pizza every day, I called that a good week. I was 30, got my blood work done, and my triglycerides came back high. And then I said, I exercise, I'm not fat. And lady goes, you drink soda and eat pizza, don't you? Hung my head. I do. Cut back. Now they're all good. Okay. And that was an important point. Even with exercise, I had high levels when I was eating poorly. So it took some changes. Okay. That's, of course, the fatty acid right there. You can see it's saturated. It's called saturated fat because it's saturated in hydrogens. And these are typically solid at room temperature because of those van der Waals forces holding them together. Whew. And the trans fats. Okay, trans fats look like this. I just drew a double bond in there, didn't I? Yeah. Did I change the shape of my fatty acid tail? I got single bonds here, and then here I drew this carbon double bond. But I didn't change the shape of it, did I? All right. Form and function really matter. Cis and trans. Okay. You got your carbon with your double bond like this. Okay. You can be across. That's what trans means, like across. So if I've got my carbons across like this, which would be, I got them backwards. Yeah. I got them backwards. Don't look at that. Oops. What can you say? This would be a trans fat because trans means across. And basically, a trans fat looks like this. So basically, what I'm trying to tell you is a trans fat looks like a saturated fat. Just turned off that page right there. It looks like a saturated fat, even though it's got a double bond in there and it's not saturated in hydrogen. So it's unsaturated, but the tail is still straight. Now a cis fat, let's draw the cis fat here, actually. A cis fat, we're going to put those on the same side, like this. And now with the cis fat, the shape of the tail does change. Okay, so why are trans fats so bad? Well, the reason why something like this is an unsaturated trans fat, what's harder to break? A single covalent bond or 2 covalent bonds? And it's not a trick question. It's harder to break a double covalent bond. Those bonds are stronger. This is a stronger bond. That makes that thing harder to break down. So now I've got basically a saturated fat that's even harder to break down than a regular saturated fat. So we call these trans fats because of the way that this double bond is created. And of course, trans fats are found in like hydrogenated vegetable oil. So hydrogenated vegetable oil, what they do is they take a vegetable oil, it's liquid at room temperature, right? And they add hydrogen to it, which means they're breaking some of those carbon double bonds, adding in hydrogen, but in the process they make trans fats. Okay. This is like what you find in Crisco, really bad foods. Try to avoid trans fats if you can. And I'm proud to say that, like, when I gave this lecture, gosh, 6 or 7 years ago, one of the pictures I showed was Girl Scout cookies, because Girl Scout cookies for years were like really bad in trans fats. People love the Crisco and the trans fats because, man, you want to make the flakiest, fluffiest crust for an apple pie or a pie or a pastry. You would use it because it's cheap and it tastes good and a long shelf life. Just turns out that trans fats have no nutritional value, none, zero, in any amount they can be detrimental. So if you ever wanted to avoid something in your life, trans fats, and going back to my Girl Scout cookies, they used to have them. They were really bad culprits, and I'd show a picture of them like, can't eat these guys. These are horrible for you. And then sure enough, like the next year after I figured out that they had that, they changed. And they didn't change because of me, I promise you. And I'm proud to say that Girl Scout cookies now are not nearly as terrible for you as they once were. Yeah.
What would be a good alternative to something like Crisco?
Just use things like, yeah, I don't know actually. I use olive oil, peanut oil. I just don't eat those kinds of foods that you would need that, except when I get chicken fingers. You know, when you go to the Southeast, man, every gas station has like these amazing chicken fingers. Ugh, I eat them all. Yeah, so bad. Yeah,
Coconut oil. Is
Co-
that-
I think that's okay. Yeah, I'm not the one that does all the cooking in the family. My wife figured out a lot of these things. So, yeah. Okay, so this is heart disease. I actually compared this to COVID last spring. Those numbers have greatly changed. But you know, we are on COVID. We're approaching 1 million people. We'll probably reach it maybe the end of this year, early next year. That's in 2 years. So we're killing. You know, COVID's taking out 500,000 or so people a year. That's largely preventable. Just get your vaccinations. But heart disease is also fairly preventable. It's a number one killer of people. 28 million people in the U.S. have heart disease. It kills over 500,000 a year, right? So, I mean, we hear about COVID deaths every day. If you go look at the New York Times, they tell you the number of cases and they tell you the number of deaths, and you can look up all this information on how much COVID has killed. And it's terrible. It's awful. But look at the numbers for heart disease today. 1.2 people every minute. One heart attack every 40 seconds occurs. They're not 100% preventable in some people, but for the vast majority of us, a little bit of change in when we eat, what we eat, how much we eat, and a little bit of exercise could prevent a lot of this. And exercise does not have to include going to the gym. I have a step counter and I go hiking as well as working out, staying active, getting your 6 to 10,000 steps a day, getting those heart points in there is good, where you actually elevate. Like fast movement is great. And of course, strength training, just gosh, one time a week, just go in there and hit like 6 sets per muscle group. And that can actually have some pretty good changes on you. Good. Yeah, and if you're like me, I'm a terrible dieter, but what I can do is portion control. Control can be hard, especially like when you're on cell phones the entire lecture. Those things just hold our attention, don't they? Okay. So take home message: fats are loaded with calories. We do need like some essential fats like the omega-3s, omega-6s. Try to switch up your saturated fats for unsaturated fats. Moderation, avoid trans fats. Okay, fat free. Be careful with that. Fat free. my hardest thing in the world to find is yogurt. Yogurt is very good for you. It's made from milk, basically, some bacteria. We know the bacteria in there are good for your gut health. It's full of calcium, proteins. The problem with our yogurts, I don't even know what to do anymore. If you go for fat-free yogurt, it's loaded with sugar. If you get the regular yogurt, it's loaded with fat. Do what's best for you. I tend to just eat the yogurt that tastes the best without as much sugar. That's how I try to go for it. So the Fage Greek yogurts are the kinds that I often go for. Just saying. That's why it's good to look under the hood, get your blood work done, and see where you're standing on some of this stuff. Okay, so we've talked about sterols, we've talked about fats. Now we're going to talk about phospholipids. And when I first started talking about lipids, and I said, lipids are hydrophobic. They're full of carbon, hydrogen. They can't form a hydrogen bond with water, but you can add these functional groups to it. So you can get part of the molecule will be hydrophilic, part will be hydrophobic. And that's amphipathic. And that's exactly what we see in a phospholipid. This is the phospholipid used to make the membranes of bacteria and eukaryotes. Did I skip a group? Anybody know the other group that I skipped? Archaeans. Yeah, when we talk about membranes, I'll show that the archaeans use a phospholipid, but they don't have fatty acids. This is, of course, a phospholipid made up of fatty acids. There's our glycerol, there's our phosphate group, here's our fatty acid tail. And as you notice, this molecule is amphipathic. Yeah. The phosphate group, of course, is what is dissolvable. It can form hydrogen bonds with water. I forgot to put my little negative signs on the oxygen. They've lost their protons, their hydrogens basically, in the pH of what's our cells. And so they'd have a negative charge. And of course, they can form hydrogen bonds with water. So this is amphipathic. Those phosphate heads interact with water. The fatty acid tails, of course, are hydrophobic, and they interact with themselves. So what happens is phospholipids, on their own, will spontaneously form a membrane. And specifically, they can spontaneously form what's known as a phospholipid bilayer. So kind of a mouthful here. But we get the name phospho from the phosphate group attached to a lipid. And then we have a bilayer. And this phospholipid bilayer, here's our phosphate heads interacting with water on the outside of the cell, interacting with water on the inside of the cell. And because the fatty acid tails are hydrophobic, they turn away from the water. They fear water. So they're moving away from the water and toward themselves, whereas the phosphate heads interact with the water, and we get this bilayer. So the bilayers, here's one fatty acid, here's another one. Here's another way to draw it. The simplest way to draw a phospholipid looks like this. This would be my phosphate head, my two fatty acid tails, and these things are attracted to each other by hydrogen bonds up here and the water up here. And of course, van der Waals forces are interacting with these fatty acid tails. That's one layer. Here's my second layer. So I have a bilayer. I have two layers now. Here's the top layer, the bottom layer. This could be outside the cell. And this is, of course, inside. Okay. Let's see what else I have here. Yeah. Okay. Got a little bit further than I thought. At any rate, this interior of the cell, of the membrane, is of course hydrophobic. And the exterior is, of course, hydrophilic. And this sets up a scenario called selective permeability. I ran out of space there. Sorry about that. Selective permeability. So what that means is only certain things can easily cross a membrane. And this is exactly what you want, right? Because if this is the barrier between a living cell and this outside world, you've got to control, you've got to regulate what enters and exits the cell. Okay, so this sets up selective permeability. Now, when you look at this picture right here, what all are you seeing? Well, just broadly speaking, just what do you think this molecule might be? What class of macromolecules? It's a protein, right? And then we've got other proteins here. And we've got some cholesterol in there. Then we got our short chain oligosaccharides. So the point here is that a cell membrane is made up of about 50% phospholipids and about 50% proteins by weight. So that tells you that all those proteins embedded in the cell membrane are doing lots of things, right? Because it's expensive to make a protein. There's a lot of work involved with making a protein and embedding it in the membrane. And a lot of what those proteins do, they're involved with all kinds of things. Moving things across the surface moving things through the membrane is one of them. This is where your active transport, facilitated diffusion, basically transport is involved. Okay, well, you look at like an animal, we're made up of 17 trillion cells or more. Well, those cells are held together, right? They're held together by different types of proteins. One of them is called collagen. It's outside the cell here and also inside the cell. And so there's lots of proteins involved with holding our cells together. There's proteins that allow for things to pass between cells. There's a lot. So just lots and lots of functions. There's also, remember we've got chemical signals traveling through our body. A lot of those chemical signals are hydrophilic. They travel easily in the blood. Well, for that to get inside of a cell, or even for the cell to receive a signal, they might have protein receptors on the surface. We learned about one just a few minutes ago, right? The receptor for cholesterol, for the LDLs. Of course, we have cells that can, they have proteins on the surface, so we can recognize self from non-self. And a lot of those are, of course, glycoproteins. That's all these short-chain short-chained oligosaccharides on there. Okay, are we good? All right. Yes.
I guess is this why like denaturation is so like detrimental to like our bodies, because proteins they're like a part of so much of this.
Oh yeah. Yeah, I mean it's important at the cellular level, and also when those proteins denature and you cool back down, they may not come back. They may not refold. They may be permanently stuck in that turned off position. And if your cells are, if they're capable, they can repair them. And we do have what are called heat shock proteins that we can use to help prevent the denaturation or repair the damage. The scary thing with like heat stroke and denaturation is in your brain, because so much of what we do is stored as memories and proteins in our brain. And if those proteins become damaged, you can have permanent damage that is irreparable. Okay, so there's our cell membrane, selective permeability. Just like Gandalf standing on the bridge of Khazad-dûm, facing down the Balrog of Morgoth, he's not letting the Balrog pass through. Now, of course, these are both of the Astari. They are very powerful beings. Now, Gandalf, he is a wielder of the secret fire. the flame of Anor. And he told him to go back to the shadows, flame of Undun, because you cannot pass. And then, of course, Gandalf cracked the bridge at Khazad-dûm, thinking he survived it. The Balrog fell and took Gandalf with him, and Gandalf fought him for days and nights until he finally smote his enemy's ruin upon the mountain. And then he was brought back by Manwë and Galadriel as Gandalf the White because Saruman had gone evil. All right, did you catch all that? Yeah. For those of you who are interested, we will have the Rings of Power coming out this fall. It will be the first billion-dollar TV show ever. Thank you, Amazon and Jeff Bezos, who has a crush or an obsession with Lord of the Rings. So we're going to see that. But despite my pop cultural reference of one of the greatest stories ever told, we're talking about membranes forming a barrier, and the idea here is that Gandalf is a barrier to the Balrog so that the Fellowship could get away and take the one true ring of power back to Mount Doom and toss it in there so that Sauron, who was corrupted by Melkor, could never have it. And what I told you is just scratching the surface of the lore of the Lord of the Rings. Oh, I'm almost out of time. Anybody have any questions? Any question about Lord of the Rings? I had a friend one time in graduate school, read the Silmarillion and took like 200 pages of notes. What would you do? Just rewrite the book? Jeez. All right. I will see you guys on Thursday. We'll continue on cellular membranes.
You should actually have this.
That's the sound effect on the PowerPoint.
What's that?